Good evening, everyone. Tonight we're going to go over the discussion board 2 for week 2. We have some more Excel epidemiology work that hopefully you can use in the field when you start working up these things in real life. So what you'll see below you is an example on how to calculate sensitivity and specificity. Once it explains, we'll move on to how to use sensitivity and specificity data along with incidence data or prevalence data to estimate how many people will be found using a specific screening program. First, let's orient you to a 2x2 table for this example. So here we have disease positive. Now this can be whatever disease you want. Diabetes, HIV, influenza, whatever you want. So when we add up everybody in this column, we get our all diseased. Now our all diseased is our prevalence or incidence numerator. Okay? All right, so that's our prevalence or incidence numerator. So that's everybody that's diseased. All well is the total population minus everybody that's diseased. So this is everybody that's well for that specific disease. And then we have test positive and test negative. So if you're in A, cell letter A, you tested positive for the disease and you actually have the disease. This is what we call a true positive. If you are in cell D, you tested negative for the disease and you are truly negative for the disease. So the two cells that we want to maximize or give them the highest number are cell A and cell D. False negative means that the test came back negative, but you truly have the disease. Now, in the old HIV testing days, we used to see these false negatives in people that were recently infected with HIV, and the time had not yet passed for them to test positive on this. So they would get a false negative result. Current research shows that in that time window in which they were told that they were negative and that they were in fact positive, they had the highest levels of viremia, so that's the highest number of virus in their blood, which meant that they were more likely to spread disease. Then we have our false positives. So this is people that tested positive for the disease and did not in fact have it. And again, if we go back to the early days of HIV, this was pregnant women. They would often have elevated antibody levels and they would test positive for HIV when they in fact didn't have it. Okay, so if we are looking at the formula based on what we've got going here, we have A over A plus C. That is our sensitivity. And I've used formulas again, and if you click on the formula, you will see that we have A in the numerator and A plus C, which is all disease in the denominator. And this is our sensitivity, okay? Now, if we go down to our specificity is a little bit different. It's D over B plus D, which we can see here. And it is the proportion that are true negative. And again, these are the two numbers you want to maximize. You want to maximize A and D. So this, as it sits, is an active formula. So you can play around with these numbers all you want. And they will change as you kind of alter the numbers in our examples. Notice how those change. So in this example, the specificity is 100%, whereas the sensitivity is 67%. So generally, what you want in a screening test, so this is administered to a large number of people, you want a high sensitivity. Okay, so you don't want any false negatives. You want to maximize the number of true positives. Okay, and in a confirmatory test, you want a high level of specificity or the number of true negatives. So you want to minimize the number of false positives. So what ends up happening is your first screening test catches hopefully close to 100% of the people, and there's no false negative. But when you catch 100% of the people, there's probably going to be some measure of false positive. Then you bring a tool that is very specific. For example, in this example, has 100% specificity, and you can show which of those tests from the first screening test are in fact true negatives. Okay, so this is a fake example. You can review more detailed examples in the textbook as they go through all these results. Now, this gets a little bit more complicated, as now we are going to apply sensitivity and specificity to a real example. Now, you can find these sensitivity and specificity calculations on anything, from pregnancy tests to drug tests to tests for HIV, STDs, or tuberculosis. Anything has to give you their lab-dictated sensitivity and specificity numbers. But as epidemiologists, we know that all diseases occur in populations, in different populations at different rates. If a disease is higher in prevalence in a given population, then their predictive positive value of number of finding their cases, or your ability to find new cases, will increase. So for example, let's go back to our HIV. If I am testing a random group of 1,000 men who have sex with men, or MSMs, I am going to be more likely to find HIV than if I were to test 1,000 men who are not MSMs. They are purely heterosexual. So that means my predictive positive value will be higher because the prevalence is higher. Okay, and then we have the negative predictive value. Okay, so I'm going to show you how to use this. So in our previous example, before I started toying with numbers, I had 90% sensitivity and 95% specificity. And once again here, I have our new laid out table. However, I've added a new layer. You can see that A equals our sensitivity and D equals our specificity. And all the numbers are laid out and tagged for how to do this. Now, in our previous example, sensitivity was A over A plus C. However, predictive positive value is A over A plus B. So we're going to go this direction. And our negative predictive value is D over D plus C. Okay. So first thing, remember, our sensitivity and specificity are 90 and 95. So we plug in 90 for sensitivity and 95 for specificity. Now, 1 minus sensitivity is this number, and 1 minus specificity. So if we took 90% away from 100%, we would get 10. Whereas if we took 95 away from 100%, we would get 5. Now we populate those values. As you can see here, we have incident number here, but you can just as easily use prevalence number as well. Does not matter. So let's say that population A had 250 per 1,000 population. So all diseased, 250 per 1,000 total population. If you take 250 away from 1,000, you get 750. That is everybody that does not have the disease or who is not estimated to have the disease in our population. The next step is rather straightforward. We're doing the exact same thing with population B, but population B has a completely different incidence rate, 3 per 1,000. So again, we distribute the 3 in the A plus C and the 1,000 in the A plus B plus C plus D. And this is 1,000 minus 3. Notice the sensitivity and specificity for this screening test are identical in both tables, because in theory, we're using the same screening test to look at population B and population A. The next step is to multiply your percentages by your data. So for example, in this situation, It is 0.9 times A plus C. And that gets you your, clicked off wrong. That gives you your numerator here. And then you multiply 0.10 by 250, and that gives you that number as well. So you're just distributing your percentages. So what this is estimating is, this is saying that in this population, population A, the disease occurs at 250 per 1,000 people. And when we apply the 90% sensitivity and the 95% specificity, it is estimating that 25 per people, when we test the entire 1,000, will be given a false negative diagnosis, whereas 38 people will be given a false positive one. Now, when we screen with that same test using a smaller population, we see that nobody is given a false negative diagnosis, and 50 people are given a false positive diagnosis. Again, once again, just distributing based on the percentages in step 3. Now, at the top of our table, you'll remember that these are the formula for positive predictive value, or PPV, and negative predictive value, or NPV. So as we scroll down in our table, you are going to notice that I have written these formula into the Excel sheet. Okay, and that calculates the positive predictive value and the negative predictive value. What you'll notice is in the higher population, the higher incidence population, my positive predictive value is 85%. Whereas in population B, the low prevalence population, my positive predictive value is very low. So I'm going to find more cases if I screen in population A versus population B. Okay, so let's say that each test costs $25, and there's an error right here, and I'm basically spending I'm doing 1,000 tests in each population. So each population costs $25,000 to screen. So I used 1,000 times 25 gets you 25,000. Well, in population A, remember, I found 225 cases. So if you divide 25,000 by 225, you get $111 per case found. So it's cheaper because you screened and you found more. However, in this example, we only found 3 cases and we spent $25,000. So each positive case cost us approximately $8,333. So this is a tough choice that public health departments have to make. Oftentimes, public health departments are moving away from screening heterosexual people for HIV. And the reason is this dollar amount here. When you screen in a population where there's low prevalence, on average, you're going to pay more per positive found. However, if you screen in a high prevalence population, you get more bang for your buck. You get more positives, which prevent more people from spreading, potentially. So if I spend $25,000 in population A, I find 225 people, potentially notify them, get them linked into care, and reduce the risk that they will transmit to 2 additional people per infected individual, which is potentially the reproductive value of HIV in the United States. So I have potentially saved 450 people from being unknowingly infected by finding 225 people. Whereas if I screen population B, I have spent $25,000 to find 3 cases and potentially only saved 6 people from getting HIV. So the case is clear. Screening in population A is a much more reliable way. Now, you are going to be completing this entire table. with your own